Hi, my name is Dennis Derrickson, and I'm a professor at California Polytechnic State University. I'm also in the electrical engineering department there. And today I want to talk about amplifiers. And if you cascade a oscillator with an amplifier, what kind of damage can the amplifier do in terms of changing the noise characteristics from the oscillator? And we're going to call that residual measurements of the amplifier. And we're going to look at both amplitude and phase noise. And so I have a very detailed outline here of all the things I'm going to try to cover today. It'll be a little longer video, but I'm just going to get started here right away. And first tell you what we're trying to do. Okay, here's the goal of this discussion. Okay, we're going to start on the left-hand side with a perfect source. And what do you mean by a perfect source? It's an AC source at a particular frequency, and it has this mathematical function of some amplitude, and it's a cosine wave, and it is a perfect pure sine wave. If you look in the frequency domain, it's a delta function. It has no spectral width, perfect source. And we're going to put it into an amplifier, and the amplifier will take that signal, amplify it up, and deliver it to, in this case, a spectrum analyzer to see what happens. So this amplifier here does not show any noise sources, but there are noise sources in that system that are going to contribute to both amplitude instability in the spectrum analyzer measurement and also frequency instability. And the goal of this presentation is how to characterize this amplifier to see how much damage it can do to the oscillator when you go through this noisy amplifier block. And what it could do at the output right here is we have the original perfect delta function that's coming from the oscillator. Since we're having gain, we're going to add just broadband noise in the amplifier. But in addition to that, we're going to find that the spectral width of the oscillator is actually degraded by the amplifier and its noise qualities. And we're going to try to do a measurement that defines how much additional width, how much additional baseband rise in the noise floor we'll have when we cascade an amplifier after an oscillator. This will be called residual, amplitude, and phase noise measurements. But there's a lot of background I have to go through before we can get to that final measurement of amplifiers. And we'll have several examples in this presentation. So first, I want to talk about the kind of diagram we typically use when we do residual measurements. So here represents the output of the cascade of a perfect oscillator and an imperfect amplifier. We have the nice original delta function. We mentioned that the spectral width of the oscillator gets wider, and then the noise floor gets higher. Those are the two basic consequences of the amplifier, making the oscillator less than perfect. And the plot we're going to make that's going to talk about what kind of damage that the amplifier has done is going to be this plot. And typically we have the script L of F describing it. It has units of dB carriers, dB from the carrier peak per hertz, single sideband noise density. And let's look at that. Okay. So first, we're going to take this little small region right here with the dashed lines, and we're going to make that region 1 hertz wide. And we're going to measure what is the noise power at that spectral bucket there in a 1 hertz bandwidth. Then we're going to compare that 1 hertz noise power to the total power on the carrier. We're going to call that dB down from the carrier. And so this plot right here is going to have on its horizontal axis offset frequency from the carrier. So here's this noise slice of 1 hertz of noise, and it's offset a certain frequency. And let's say that that is 1 megahertz offset from the carrier. We'll take that power, compare it to the carrier power, and we'll make one plot right here showing a point at a certain offset frequency. Then we'll go to a different offset frequency. We'll measure the dBc, go over here and plot it. Now, I show you here a typical result of what happens when we do this residual phase noise and amplitude noise measurement. We get this floor at some frequency, which represents kind of the has to do with how much gain this amplifier has. And anytime you have gain, you're going to amplify noise. But then you also get this rise at low frequencies. Here it shows it starts at 10 to the fourth hertz, 10 kilohertz. But it could start at other frequencies. And this has to do with the fact that most amplifiers have 1 over F noise. And normally that wouldn't be a problem. 1 over F noise is at very low frequencies. Why would it pollute something that's at gigahertz frequencies? But there is a nonlinear phenomena where this low frequency noise can actually modulate itself onto the high frequency carrier. And we get this 1 over F noise region right here where the power rises as 10 dB per decade going below some frequency where it intersects the broadband noise. So these plots right here, these are the plots we're going to use to characterize how much degradation the amplifier has to a perfect oscillator. And we're going to call this the residual noise plots. And we're going to be able to separate the noise that's due to AM modulation, and we're going to separate the noise that's due to FM modulation. So we'll have plots like this that are for the AM noise contribution, and plots like this that look at the FM noise contribution. And we'll see many examples of that later in this presentation. So just a little overview on what is the nature of the pollution, the noise sources on this amplifier. So we have a perfect source right here, and we're going to add noise to that. And so we'll have zero crossing noise, which we call jitter, and we have amplitude noise right here. And so both of those are things that happen when we have an amplifier cascaded beyond a perfect amplifier. We can do that in the probability domain too. So here we have time in this axis, voltage. And so if we do a histogram on this zero crossing right here, we can get a jitter profile for this imperfect oscillator waveform. Then if we look at the peak right here and do a histogram right there, we can get a statistics on the amplitude jitter. So both amplitude jitter and time jitter, which is also related to phase jitter and phase noise, are illustrated in this plot. Now, in earlier presentations, I've gone through lots of transistor level and below analysis of noise. And so here's an example of something that's from a previous presentation looking at the noise performance of an amplifier. Here's a bipolar junction transistor amplifier, and we model it, and it has thermal noise on the base. It has shot noise on the base emitter junction, shot noise in the base reflector junction. We have to calculate all the noise sources. We have to propagate them individually to the output to compare them at one point in the amplifier. And it's involved. It's very instructive, but it's very involved. And sometimes at the high level of an amplifier, we want to deal with that. So what we'll do is we'll come up with a black box model. And the black box model for the gain stage is just having some input resistance, some output resistance, and some voltage gain. This is a dependent voltage source where the output voltage is some constant AV times the input voltage. Of course, this black box gain stage does not have any kind of noise source with it, so we'll have to add noise sources with it. And so what we'll do is we'll have a black box module that will add 2 new noise sources right here to model the noise effects of the amplifier. The first noise source we're going to look at is going to be a thermal noise. We're going to say that this input resistance of the black box has thermal noise. And here is a formula for thermal noise, that the RMS value is going to be the square root of 4 times K times T actual, the real temperature of that resistor, times the bandwidth divided by the input resistance. And then we're going to add one more noise source. We're going to pretend that it is another thermal noise source, but in actual fact, it models every other noise source in the system. It could be shot noise, could be thermal noise, could be 1 over F noise, but we're going to pretend it has the same mathematical form as a thermal noise would have, but we're going to have this fictitious number right here. It's just really a variable that allows us to fit the noise level. And we're going to call it the excess noise temperature. And so this one source right here is going to model every other noise source except for the thermal noise of this resistor right here. We're going to say that our output resistance has no noise, and with these two parameters, we'll be able to model the entire noise performance of this amplifier. The excess noise temperature can be really hot. It's not a real temperature. You can have thousands of degrees of excess noise temperature. It's just a fictitious parameter that we fit into the thermal noise model. There's a couple other parameters. Noise factor is going to be 1 plus the excess noise temperature over the actual noise temperature. And if we take the logarithm of that, we can get the noise figure. So the output noise right here is going to be some linear gain right here times the input noise. This is a signal. And then the output noise is going to be this total current right here times that input resistance times the voltage gain. So both the signal and the noise are amplified in this black box noise model. Here's an example of using the black box model where we're going to cascade two amplifiers. Let's say the amplifier has 20 dB of gain, a noise factor of 2, and a noise figure of 3 dB. We start and make a plot showing signal power and noise power on this axis, and this horizontal axis is position in the cascade. This resistor right here, we'll assume it's a 50 ohm resistor right here, its thermal noise level is minus 174 dBm per hertz. So I draw this noise level here at minus 174 dBm per hertz. Then we have this signal level here at minus 40 dBm. And then we enter the second stage right here, and the second stage has all this noise associated with the input resistor. Since the noise factor is 2, that means the excess noise temperature and the actual noise temperature, the actual temperature are the same. These will then add together, and we'll get a noise figure of 3 dB. So if we have two equal noise sources and they add together, noises add as root sum of square, or in powers, they add up by doubling. And that's a 3 dB increase of input noise power. So that's minus 171 dBm per hertz. The signal's at minus 40. The difference is the signal to noise ratio. We have 141 dB signal to noise ratio. We then amplify in this first stage. And so we increase the signal by 20 dB. We increase the noise by 20 dB, giving an output signal of minus 20 dBm and an input noise from the previous stage at minus 151 dBm per hertz. The input noise sources for the second stage are identical to the input noise sources right here. And so that's minus 171. So much smaller than the minus 151 from the previous stage, it doesn't matter. So these two noise sources play no role in the noise performance of this system. And finally, we amplify to the output, giving you a 0 dBm signal in the load and a noise from the amplifier at minus 131 dBm per hertz, but still we have 141 dB of signal noise ratio. So this is just a little quick thing about black box noise analysis, showing how gain and noise cascades through a system. Let's go and remind what we're trying to do right here. We're trying to characterize how much damage this resistor does to a perfect oscillator, and we're going to measure that in a spectrum analyzer. We want to find out how much my performance can be affected by noise from the input source right here, or we could have noise sources coming in from the power supply too. All those could contribute to degradation of the signal in this amplifier. So let's, to get going right here on the more detailed analysis of residual phase noise, we have to go back and understand AM, FM, and PM modulation theory a little bit with sinusoidal modulation. So the amplifier is fighting against phase noise contributions and amplitude noise contributions, and let's kind of look at that battle in a little more detail here with modulation theory. Okay, so here we're going to have just kind of like the basic forms of AM, FM, and PM modulation all kind of collaged into a single page right here. So a general waveform, the voltage as a function of time is going to have some DC amplitude, and then it's going to have a time varying amplitude if you have AM modulation. And then we'll have phase modulation, and the phase of the signal can be changing versus time. I don't show it right here, but also the frequency can be modulated versus time. And so we're going to consider only sinusoidal modulation right here. So here is my modulation for AM. Here's my modulation for phase modulation. Here's my modulation for frequency modulation. And then we also will come up with some constants that are used in sinusoidal modulation: the AM modulation index, the phase modulation index, and the frequency modulation index. And there's also a couple of things that will be handy. One is saying that the frequency is the time derivative of the phase with respect to time, radians per second, and then phase is the integral of frequency times time. So radians per second times seconds gives you radians right here. And then when we do all this, we're going to have some trig identities that'll be important to when we substitute these modulations into the general waveform. We're going to use these trig identities to help simplify things. So these are all in communication books. I'm trying to just distill it into a short little review. So let's look at AM sinusoidal modulation. So here's a general waveform mathematical equation for amplitude modulation. And with some substitutions for AM modulation and some trig identities that are used and some assumptions, we come up with this final answer here for the AM modulation, where we have a carrier, we have a upper sideband and a lower sideband if we have a sinusoidal modulation frequency. Now, in the time domain, what we have right here shows this high frequency carrier right here, which is associated with this AM amplitude. So the amplitude of the AM is just the mid-range value of the amplitude, but we have modulation on it, so we have some peak value of the modulation right here. If the AM amplitude and the peak modulation are the same, that would be called a 100% modulation index. Here's the modulation index talking about the ratio of AM peak divided by AM amplitude. So this is a time waveform. In the frequency domain, we have the carrier, which has the AM amplitude, and then we have upper sideband and lower sideband, which is going to be half of the AM peak and amplitude, or if you compare the two, it's just going to be the AM modulation index divided by 2. So I know this is a quick overview, but I just wanted to have you see it again if you haven't seen it before. This is going to be the most important thing for residual phase noise to understand. If we have AM modulation, we have a carrier and 2 sidebands. It's often instructive to do it, a view of this in what's called the IQ domain, where we view these each as vectors with magnitude and phase. So this is at some center frequency like 1 gigahertz as an example. And we're going to put it into a complex amplitude IQ domain display. Here we're going to essentially strobe the carrier at 1 gigahertz. Normally this carrier will be rotating around the axis as phase advances, but we're going to just freeze it by strobing it at the frequency of the carrier. And then we're going to take these 2 vectors right here, and we're going to add them to the carrier vector. And these are again being strobed at a mega carrier. So the upper sideband is a little higher frequency. So it's going to, this amplitude represents the amplitude of this upper sideband, and it's going to rotate around this point right here at the modulation frequency. The lower sideband has a lower frequency, and it will rotate clockwise. And these 2 sidebands in AM are in phase, and so when you add all 3 of these vectors together, you get this arrow shown right here. So it's always going to go back and forth on the axis right here, changing the amplitude. So that is a IQ domain version of AM modulation. Looking at phase modulation, we're only going to consider the case where the amount of phase modulation is small, which is what we're going to be doing when we have noise modulating the carrier. Start out with a generic waveform for a phase modulated signal. We plug in the phase modulation form for the modulation frequency, do some assumptions that the peak phase deviations much less 1 radians. And if we do that, we get these things very similar to AM modulation. We get the carrier frequency, we get a upper sideband and a lower sideband, but we get this minus sign right here. So the lower sideband has a 180 degrees phase shift. So if we took the AM modulation IQ result right here, which would be this vector and this vector, then we take the lower sideband, negate it, we get a vector out that's now in that direction. And so this one's going clockwise. It's a lower frequency. The upper sideband's going counterclockwise as a higher frequency. And you can see that the resultant vector will always be perpendicular to the carrier vector. And so this resultant vector will go from positive to negative in a phase modulation kind of peak. And the angle right here is just going to be the peak phase deviation you have in your modulation. That's the angle that you'll have for this phase modulation. This is the IQ domain viewpoint of phase modulation. Frequency modulation is very similar. In the case of very small frequency modulation, we get a very similar case. We get a carrier, an upper sideband, a lower sideband, and the lower sideband's out of phase with the carrier again. For small phase modulation, the only difference is that the peak phase deviation is the FM modulation index. And the FM modulation index is the peak frequency deviation over the modulation frequency. And that is the same thing as the peak phase modulation. So that's a simplified version of FM, a spectral domain view, and a IQ domain view. Again, this is for the FM modulation index less than 1. We have higher modulation index, becomes much more complicated and takes many more pages to go through. But from understanding residual phase noise, these small phase fluctuations and amplitude fluctuations and frequency fluctuations are what we need to know. Okay, so let's get to understanding residual phase noise. So if we have an amplifier with a perfect one frequency with no width to it, and then we put an amplifier after it, one thing that amplifier is going to do is it's going to raise the noise level. So here's an example of a noise power in dBm per hertz. And so thermal noise power is minus 174. So this noise right here is 20 dB above the thermal noise. But what we're going to do is we're going to pretend, we're going to do some pretending here. So all this noise is controlled by the amplifier, and we're going to take this noise right here at a positive offset frequency and this noise at a lower offset frequency, where they're the same offset frequency. And even though it's noise, we're going to pretend it's actual real modulation signal, which is not true, but we're going to just say that these two sidebands, each 1 hertz width in these dashed lines is going to be a additive noise, which is going to look like both AM and FM modulation on the carrier. Well, this is additive, it's a linear system, but we're going to pretend that it does a modulation function. So if we have this black box noise model here, where we have thermal noise and excess noise going to the input, amplified to the output, the IQ domain viewpoint of that's going to be that we have the signal right here, which is amplified, which is this long vector right here. And then the excess noise and the thermal noise will be vectors that add in random directions right here. So sometimes we have FM or phase modulation, sometimes we have AM modulation, so it just happens randomly versus time. So an amplifier, even though it's not modulating the signal, we're going to view the noise as if it were just putting both AM modulation and phase modulation onto the signal, degrading its performance. So these sidebands right here, although they're noise and not modulation signals, we can kind of view them as having both an AM noise personality right here, where the two sidebands are always adding constructively and are in phase with the carrier. Or we can view the noise sidebands as being phase modulation in nature, where we have two sidebands that are adding perpendicular to the carrier. And so if we look at that, we can say that the thermal noise power right here has both phase noise and amplitude noise personalities. So if we do that, the amount of phase noise we're going to have right here from this broadband noise is we're going to look at the peak value of the noise power, of the noise voltage, compare that to the peak value of the signal power. And then we're going to take and use the arc length formula to show that the peak phase deviation is going to be just twice times the sideband noise level right here. This is a sideband noise level right here, divided by the carrier level. So if we have a certain noise level, we can figure out how much peak phase deviation that is having. In addition to that, we can also view this noise as half of the noise being amplitude modulation, where the two sidebands of the noise are being in phase with the carrier. And so here we have expression showing that we have a carrier plus a sideband that is AM modulated, lower sideband, and an upper sideband. So we're taking this noise and pretending it's modulating the carrier and coming up with how the noise contributes to a phase modulation, how the noise contributes to an amplitude modulation. So this plot right here is supposed to show, if I just did a spectrum analyzer plot from low frequencies to high frequencies, we have the carrier right here, which is supposed to be a perfectly infinitely narrow function from the oscillator. But then we have the amplifier that contributes this broadband noise right here. And we just analyzed the fact that these offset frequencies from the carrier can be thought of both causing AM and phase modulation onto the carrier. But we also mentioned that there's this phenomena called 1/f noise. So here at low frequencies like a kilohertz, 10 kilohertz, 100 hertz, 1 hertz, that exists too. But normally in a linear system, that would be don't care. You could always just high pass filter your amplifier, and this 1/f noise should have no effect on this noise right here. The only thing that should matter is just this noise offset from the carrier. But if you have a nonlinear system, and these amplifiers are nonlinear, we will get modulation of this low frequency noise right here onto the carrier. And that's unfortunate, but it turns out that in high performance oscillator design, this 1/f noise turns out to be actually very important because it's at low frequencies and it gets modulated onto the carrier. So let's see, how is it that this 1/f noise can get modulated onto the carrier? Because normally a linear system, it shouldn't do that. We could just high pass filter out the low frequency noise and it would be gone. So the phenomena is some nonlinearity, and let me just illustrate a nonlinearity here. This noise right here, especially this excess noise right here, will create a voltage across the input right here. And at the transistor level, the fact that this noise is going up and down in amplitude will make slight bias changes in the amplifier. So example, there's typically a capacitance from the output to the input of a transistor. And so this noise right here will modulate that capacitance a little bit and change the amount of feedback, changing the gain of the system. So noise with nonlinearities, essentially AM to AM, AM to PM kind of conversions, will cause the gain of the amplifier to be time dependent. Previously, we just thought of the noise just adding on. This is just adding on noise right here, additive noise. But with nonlinearities, then we get gain being noise dependent. So here I show over time, the gain of the amplifier can change its magnitude and change its phase. And onto that, we also have additive noise right here. So the nonlinearity is what causes this 1/f noise to get modulated onto the carrier because of this nonlinearity, and we have gain noise right here in addition to the additive noise. So I wanted to justify why 1/f noise is actually important for oscillators, where on first pass, you would think that it would have no effect at all on the oscillator, since we could just high pass filter out the 1/f noise at a gigahertz frequency, center frequency. So that was my introduction to residual phase noise. Again, residual phase noise talks about what additional degradation does an amplifier make for an oscillator. And we're going to use these L of F plots, single sideband phase noise measurements to quantify that. So we have this instrument called the SSA-X with Keysight, and it is a one that can measure residual phase noise and actually resolve it both into its AM and to its FM and phase modulation components. If you bring up this personality, here's the block diagram that it comes in with. You have a source, and the source is divided into two equal paths right here. These two paths have the same gain, and what we're going to do is we're going to introduce the DUT into one of these paths right here. So this will be a source right here. That will be a very good source. This is the best source we can get. We're going to split it into two, and so whatever non-perfection this source has, this will add a little bit more non-perfection. But here we have an asymmetry between the two channels. We've got this channel without the DUT and a channel with the DUT. So we at the output right here, you're going to get just the source noise plus this channel noise. You get the source noise plus channel noise here, but you get this additional noise called the DUT noise. And that's what we're trying to characterize. Here's what we're trying to get, is how much additional noise does the device under test add? And this receiver uses cross-correlation techniques. So if we wait long enough, the fact that the noise source right here in this channel 1, the noise source in this channel 2 are uncorrelated. So if we do a cross-correlation between the two, we should be able to cancel out any kind of noise of these two channels. But the DUT right here is only in one channel, and so it's not going to be cross-correlated out. And so we're able to pick out the characteristics of the residual phase noise of this amplifier separate from the noise source and the channel 1 noise and the channel 2 noise. And there are some other application notes that go into this more detail, but I just want to show us that the correlation receiver is the key thing that makes this all possible. So I want to just show some example measurements of what this residual phase noise measurement looks like. So we go into this residual phase noise measurement mode as shown on the previous slide, and I have some various different amplifiers. So this is an amplifier I had in my lab right here. It's a older Hewlett-Packard 2 to 20 gigahertz amplifier that's kind of built-in power supplies and end connectors in and out. And so what is the characteristic of that? Well, so I'm going to look at this has a vector network analyzer that goes to 54 gigahertz, and so let me look at the gain of that amplifier. So I do just a through line calibration. I didn't bother doing the short open load at the input and output, so I get a little ripply in the response here, but it was simple and fast. And so this amplifier has a gain between 20 and 30 dB, going from 2 gigahertz on the low end out to 20 gigahertz on the high end. So pretty high gain amplifier. And so let's do a residual noise of this. Maybe I'm going to do a couple of frequencies. I'm going to do one at 19 gigahertz in the end and one at 15 gigahertz in the middle, and see what we get. And I want to point out that the noise contribution you get depends on the linearity of the amplifier. So if you have a low input power, you can make this happen in a linear mode. If you have a high input power, you can have the gain saturate. And the residual performance of this system can change depending on whether you're in the linear mode of the amplifier or you're in the saturation mode of the amplifier. In this case, the amplifier is not in saturation. It's not having gain compression. And so here's an example measurement. At 15 gigahertz, I'm going to put minus 17.94 dBm input. And that shows right here, we have minus 17.94 dBm. It measures it. It's an internal power meter. We have output power of 5.1 dBm. This amplifier is capable of like 23 dBm, so we're far away from saturation. So let's look at this axis right here is our units of dBc per hertz. residual phase noise. And then I have offset frequency from the carrier. This is 10 megahertz right here, and this is 10 millihertz. So 10 millihertz to 10 megahertz offset frequency from the carrier. So here we have kind of a broadband noise floor right here at the order of minus 155 dBc per hertz. And then as we go lower in frequency, then we start seeing this rise. And this rise here is due to 1 over F noise that's getting modulated onto the carrier. That's that nonlinearity thing. Even though it's in the linear non-saturated region, there are AM to PM conversion mechanisms that still have nonlinearity even at these low input powers. So here's the noise floor is rising right here. This orange area right here kind of shows the floor of this measurement. The more correlations we do, the better noise floor we get. So here's an example of a residual phase noise measurement right here. So here it shows PN for phase noise. We can also measure amplitude noise separately from phase noise and resolve them both individually. Okay, let's look at a different kind. That was just an introduction to the phase noise, residual phase noise measurements. Here's a second amplifier I put on the system right here. It's a very broadband amplifier, only has 3.3 volts input. And this is an internally fabricated, there's a wafer fab at Keysight Santa Rosa, and they made this custom 5 gigahertz to 40 gigahertz amplifier. And so it has low phase noise as it's advertised right here. So let's look at its residual phase noise. So first we do the gain measurement using the vector network analyzer. So I only had SMA connectors here, so at high frequencies up to 50 gigahertz, a lot of this is due to the fact that I'm using SMA connectors that are only really good to 18 gigahertz. But we see that this amplifier has a gain of about 12 dB. And here I use a response cal too. I didn't do the short open load cals, so we get a little extra ripple that we wouldn't normally have to have if we did a full short open load through calibration. Okay, let's now do some other measurements. I did a gain compression measurement. That particular amplifier has a drop in gain from 12.4 down to 11.4 here at input power of minus 2 dBm. So that's the input power at gain compression of minus 2 dBm. So I want to make sure to stay out here and do the linear measurement of the phase noise. And here's the phase of the amplifier versus input power. So I do this because when we have noise, there's both amplitude noise and we have phase noise. So amplitude noise can cause gain modulation for this to go up and down, and then phase noise can cause phase modulation. So these constants are important in measuring and characterizing residual phase noise. Okay, so what I did here is I first put just a through line in place, and I have minus 5 dBm of input power, and I just do a through line, which shows like what's the smallest signal that we can kind of see. And here I'm also doing both phase noise measurements right here and AM noise measurements right here. So I've got 4 plots. One are the residual, the AM and PM noise residual of just a through line, no amplifier at all. And then I have the AM and PM noise contributions with the amplifier in place with a 12 dB gain amplifier. And I'm doing this at a frequency of 19 gigahertz with minus 7.2 dBm input power and 4.3 dBm output power. These are the number of correlations I'm doing right here. I have a big listing of all the values at different frequencies. This actually, it's hard to interpret this, if you don't have a good feeling for what good and bad is for residual phase noise, but this is actually very good. The fact that the residual noise is not that much worse than a through line. And the through lines is the best you're going to do. That should have no degradation, and the We get a small degradation in this area right here, but out here, not much degradation at all. So this is a pretty good low phase noise contribution amplifier. I looked at another amplifier right here. This is called the CMD274 amplifier. It's a little PC board version of it right here. You can see you got coplanar waveguide input, coplanar waveguide output, and brought input and output on SMA connectors. And let's look at that. It's supposed to be a wide bandwidth amplifier with low phase noise, is it being advertised right here. And it goes 2 to 20 gigahertz, and low phase noise is one of its key application features in its data sheet. So I first measured its gain response at a small input power here. I was putting in minus 15 dBm. And so the gain right here is going from 2 to 20 gigahertz with about a 15, 16 dB gain in this amplifier. Now, if I put in more input power here, I'll start getting some drop in gain. We'll get the same overall shape, but the gain's going to drop. And here we have 5 dBm input power, so we're going deep into saturation right here. Here's the nonlinearity measurement of both magnitude and phase, showing gain versus input power and phase versus input power. And this is useful in predicting the degradation of the amplifier by AM to PM and AM to AM conversion factors, which I'll go into a next presentation on that. And here's an example of measurement where we have linear performance. This is where we have a relatively small input power and only producing 7.7 dBm output power. So this is definitely in the linear region. It's not being gain saturated. And so here again, I show the noise flow with the through line right here. And then I show both an AM and PM noise level, the residual AM and PM noise contribution that shows here. And it's interesting how sometimes the phase noise is a larger contributor when you go to a higher frequency than the AM modulation is a larger contributor right here. So this is AM right here. This is phase modulation. So at beyond 100 kilohertz, AM modulation dominates. Below that, phase modulation dominates in the degradation of this amplifier. But still, it's a pretty good amplifier. And you also start seeing the 1/f noise contribution. I've done 50 correlations right here. If I want better signal-to-noise ratio, I can raise the correlation number. It takes more time, but I'll get a better margin against the noise floor measurement right here. So pretty good amplifier. And I just want to show you that as you change the bias condition, the nature of the noise can change. So that's one of the things you want to characterize in the residual performance of your amplifier. Here we have 15.1 dBm of output power. And here it shows that the AM noise now is dominating everywhere. The AM noise is stronger than the phase noise at all frequencies offset from the carrier right here. So that's interesting. A change from the fact that when it was operating in a linear point of view, we have 15.1 dBm of output power here. So we're starting to get gain saturation. And now we're getting lots of gain saturation right here. And we still have more AM noise than we have FM noise coming out of this. So the point there is that you don't want to measure the performance of your amplifier just at one input power. You want to see how it changes with different input powers. And you want to see what fractions of it is AM and what fraction of it's phase noise modulation. So it was a long presentation there, but I wanted to kind of do a summary, quick summary. So the topic of this presentation was residual phase and amplitude performance of an amplifier. We started out with the perfect amplifier right here with no spectral width, no amplitude modulation at all, no phase modulation. We go through an amplifier. This amplifier has all kinds of noise mechanisms, thermal noise, shot noise, 1/f noise. And we're going to model it as a black box noise source right here and a black box gain source. And the output right here will be wider in spectral width. It will have a broadband noise increase. And we're going to find that 1/f noise in this amplifier gets modulated onto the carrier, and that the broadband noise also produces AM and PM noise. And the output of the signal right here is going to be slightly degraded compared to the input signal right here. But there are techniques to make this amplifier perform as good as possible. You want to make sure that its AM to AM conversion constant as low as possible. Its AM to PM conversion is as low as possible. The performance of this system changes as you go from linear low input signal power to a high input signal power. So you want to characterize how the AM and PM noise change as you change the input power. Another thing you want to understand is that, and I'll show this in future slides, that the power supply right here can also contribute noise. And so if you're not careful, it turns out that if you have a very noisy power supply, it could be that the power supply noise is a dominant noise source, not the internal shot noise, thermal noise, and 1/f noise. So I hope I gave you somewhat of an introduction here. It's a more complicated field, but I wanted to show you what this residual phase noise measurement and amplitude measurement looks like and how you might characterize it with an advanced instrument like the Keysight SSA-X. So that's the presentation for today. In the future, I'm going to kind of go into more detail about the power supply and how it affects this amplifier, and then also the AM to FM, AM to PM, and AM to AM noise conversion characteristics that you can find in these amplifiers. Thanks again.